In this video, I'm going to solve fundamental problems for statically determinate structure from 7 to 10. For the first problem, we need to determine horizontal and vertical component reactions at pins A, B, and D. And joint C is a fixed connection, therefore we don't have to divide the section BD into two member sections. And for this whole video, we can assume counterclockwise as our positive moment, left to right as our positive horizontal force, and going up as our positive vertical force. Okay, let's draw the free body diagram for this problem. For member AB, we have horizontal and vertical component at point A because it's a pin connection. Similarly, we have a pin connection at B, therefore we can have two components, horizontal and vertical. And we have a uniform distributed load, which we are going to convert into a point load. And to do that, we need to first of all find the length of AB, and we can simply use Pythagoras theorem to find the value of this length, so which is going to be 3 squared plus 4 squared. Solving this, we get 5 meters. And we know that our uniform distributed load is simply the value times by the length of the uniform distributed load. That's 5, so therefore it becomes 15 kilonewtons. Okay, and let's draw the free body diagram for member BD. Okay, and we know that we need to have opposite directions for our reaction forces at point B. And we know there's 2 point loads, 8 kilonewton each, and they are 2 meters apart. Similarly, we have a pin connection at D, so we're going to have two reaction forces, vertical and horizontal. Okay, let's solve for member AB first, and then we'll go over member BD. For member B, let's take a moment about the point A. Our point load is 15 kilonewton and it's working clockwise, therefore it's going to be negative, and it's 2.5 meters away from our point. And then our point B has 2 force reactions. Let's do our horizontal parts going in left to right, therefore it's negative, and it's 4 meters away from our point, and our vertical member is doing clockwise as well. So our BX is doing counter, so this is going to be positive. Our BY is doing clockwise, and it's going to be negative, and it's 3 meters away. All of this is equal to 0. Simplifying this equation, we get 4BX negative 3BY equals to positive 37.5. And we're going to assume this as our equation 1. Now let's solve for member BD. And we can take a moment about the point D. So we know we have 2 point loads, 8 kilonewton. First load is 8 kilonewton and working counterclockwise, it's positive, therefore. And then it's 2 meters away. Second point is 8 as well, and it's 4 meters away. And now we have our reaction forces. Those are working clockwise, therefore both will be negative. And our BX is 4 meters away, and our BY reaction is 6 meters away, and both are equal to 0. Let's simplify this and solve for BY in here. We have 8 times 4, 32, plus 16, 48. And then we have a positive 4 BX divided by 6. And multiply both sides with the negative, so 48 becomes positive, and positive 4 BX becomes negative 4 BX. And we're going to assume this as our equation 2. Now we can sub equation 2 into 1. So we have 4BX from equation 1, take away 3 times BY from equation 2, divided by 6 equals to 37.5. 6 divided by 3 is 2. Taking the lower common denominator, we get 8BX. Take away 48 plus 4BX equals to 37.5 times 2 is 75. Simplifying or solving for BX, we get 75 plus 48 divided by 12, you get 10.25 kilonewton. Now we can solve for By, which is going to be subbing our value of Bx into our equation 2 divided by 6. And we get 1.167 kilonewton. Now we can sub the value of Bx into our equation. Actually, we got all the values. Now we can take some of the forces in x direction for member AB. And we know we just found the value of Bx, which is negative 10.25, and plus the value of Ax, and then plus the value of our point load in the x direction. So it's 15, 4 divided by 5 equals to 0. So therefore our value of Ax is negative 1.75 kilonewton. Now we can either have the value as negative 1.75, or we can change the vector sign and have it as positive 1.75 kilonewton. Either way, the answer is correct. Now that we have these, we can try to solve for our value for Ay. So it'll be simply taking sum of vertical reaction forces. So we know our value of By is 1.167, and it's in negative direction. And then we have negative direction for our point load, 3/5, and then our vertical reaction for A is positive. Solving for Ay, we get 10.167 kilonewton. All right, so now we have all the reactions for member AB. We are just missing reaction forces for point T. To solve for that, we're going to have to go back to member BD, and we can take sum of forces in x direction. So we know the value of Bx is positive 10.25, and then we have a negative value for our dx equals to 0. Solving for this, we get our value of dx as 10.25 kilonewton. And now we can do the sum of reactions in vertical. So this becomes, so our dy in here we are assuming as negative because it's in going downward direction. And then we have 2 point loads, 8 each. And then our vertical reaction for By is a positive, and the value for By is 1.167 kilonewton. Okay, solving for this, we get value of dy as negative 14.8 kilonewton. We can either have it as negative 14.8 kilonewton, or we could change our vector in upward direction and have it as positive 14.8, and answer is correct either way. For this problem, determine the components of reaction at the fixed support D and the pins A, B, and C for the 3-member frame. Okay, let's draw the free body diagram for all these. Let's start with member BC. Member BC, we have 2 point loads, 2 meters apart. We're going to have reactions By and Bx. On B, similarly, we're going to have 2 reactions in the opposite direction. I'm going to assume for our point C, because both of these are pin connection, by the way, if I haven't mentioned it earlier. I'm going to assume C as going up as well, but we don't have to worry about. Our equation will automatically adjust the vector directions afterwards once we finish solving it. Okay, we have a point load 4 kilonewton, for member AB. And here we're gonna utilize opposite vector of whatever we had for member BC. So BX will be going right to left, and BY will be going downwards. AY will be going up, and our AX I'm going to assume going left to right. Similarly, for our member CD, we'll have opposite reaction forces to the member BC. And for member D, since it's a fixed support, we're going to have three reactions here. So we're going to have horizontal and vertical. And then we're also going to have a moment, and I'm going to assume counterclockwise as a positive moment here. Let's solve for member AB. I'm going to take a moment about the point A. Member, the point load 4 kilonewton is acting clockwise, therefore it will be negative 4 kilonewton, and it's 3 meters away from the point. And then member BX is working counterclockwise, that's positive, and it's 6 meters away, equals to 0. Solving for member BX, we get positive 2 kilonewton. And we can write it down here, 2 kilonewton. Okay, now we have that. We can solve for our member AX, or horizontal component, at point A as well. So let's take a moment about point B. Member, or point load 4 kilonewton this time was working counterclockwise, therefore it's positive, and it's 3 meters away. Member AX is working counterclockwise as well, and it's 6 meters away. Solving for AX, we get 2 kilonewton, negative 2 kilonewton. Now, we can either have it as negative 2 kilonewton, or we could change the direction of the vector and have it as 2 kilonewton, positive 2 kilonewton. Either way, solution is correct. But I'm going to continue with our negative so that I'm consistent, and my formula will take care, my equations will take care of it, so I don't have to worry about the vectors as long as I'm consistent. Okay, now working on member BC. I know there aren't any forces working in the horizontal direction for member BC, therefore we know that whatever our member reaction for point B is in the horizontal direction, it's going to be same for horizontal direction for point C. In this case, it will be 2 kilonewton. Okay. Now let's take a moment about point C to solve for, remember, BY. There are 2 point loads. One point load is 2 meters away, the other one is 4 meters away, and both are working counterclockwise. Remember, BY is working counterclockwise, therefore it's negative, and it's 6 meters away. All of this is equal to 0. Solving for BY, solution becomes 6 kilonewton. 6 kilonewtons. Now, take a moment about the point B to solve for CY. This time, both point loads are working counterclockwise. Both are 2 and 4 meters away. Point CY is 6 meters away, and it's working counterclockwise. Solving for CY, solution is positive 6 kilonewton. Going back to member AB and summing the forces in vertical direction, I should be able to find the value of vertical component of point A. So vertical point A is, we are assuming, as positive, and vertical component for we were assuming negative, which is 6 in this case. Solving for AY, we get 6 kilonewton as our answer, and it's positive. So therefore, we did assume the right direction for our vector. This is 6 kilonewton, 6 kilonewton, 6 kilonewton. All of the vectors have been found except for vectors or reactions, you can say, for point D. Going to member CD, summing the forces in horizontal direction. Cx here is known, and it's going left to right, so that means it's positive. And it's 2 kilonewton. Take away dx equals to 0, solve for horizontal direction for point D. We get 2 kilonewton as our solution. Now taking the moment, well, before moment we can also find the vertical component for point D. So that's going to be negative 6 kilonewton for vertical component for point C, plus dy equals to 0. Solving for dy, solution is 6 kilonewton. And now taking moment about the point D, we have moment at D, take away the point load at C in horizontal direction, that's 2 kilonewton, and it's 6 meters away, equals to 0. Solving for moment D, it's 12 kilonewton per meter. Determine the components of reaction at fixed support D and the pin A, B, and C of the three-member frame. To solve this problem, let's do our free body diagram. I'm going to start drawing member BC. For BC, we have horizontal and vertical component reaction forces. Similarly, we have horizontal and vertical component reaction forces for point C as well, because both of these are pin connections. We have uniform distributed load over this member, and we know this is 2 pounds per foot, and we know the length of this member is 8 feet, so 8 times 2 is 16. So our point load would be 16 pounds, and it'll be located 4 away from each side. Now I'm going to draw member AB. For member AB, we have a similar situation. We have a pin connection on both ends. We have to make sure that we are drawing opposite vector to whatever vector we have drawn for point B, so they cancel each other out. Similarly, we have horizontal and vertical components, and finally we have our member CD. Similar idea for pin connection C, but for point D, because it's a fixed support, we're going to have 3 different reactions here. So we're going to have the usual horizontal and vertical reaction, and then we're going to have a moment around the point D. To solve this problem, let's start with member AB. We're going to take moment about the point here. Oh, and another thing I've done it, we have 0.5 pounds per foot uniform distributed load. So we have to convert it into point load here. 0.5 times 6 is 3, and it's halfway through, so 3 feet on each side. Okay, so first we have a point load of 3 pounds times 3 feet from our point A, and then we have counterclockwise horizontal direction at B, and it's 6 feet away. Solving for this, you get value for Bx as 1.50 pounds. Now, moment about the point B. This time, the point load is acting counterclockwise, therefore positive, and it's 3 feet away. We also have our horizontal component acting in counterclockwise for A, and it's 6 feet away, all equals to 0. Solving for this, you get Ax as negative 0.5 pounds. So here we found Bx to be 1.5 pounds, and our Ax equals to negative 0.5. or we can change our vector and have it as positive 0.5 pound. But for this specific problem, I'm not going to worry about switching the vectors. I know my formula and my numbers will take care of the signs, and as long as I'm careful and do not mix anything, I should be fine at the end. For member BC, we know the value of horizontal component at B, therefore we're going to take moment about the point C. Point load is acting counterclockwise, and it's 16 pounds, and it's 4 feet away. Then I have a vertical component, 4B, and it's 8 feet away, all equals to 0. Solving for By, I get negative 8 pounds, which, as we have done before, it can be either said as negative 8, or vector direction could be changed and consider it to be 8 pounds. Both ways are correct. Now, moment about the point B. Point load this time is acting clockwise, and it's 4 feet away. Remember, CY, or vertical component, is 8 feet away. And solving for this, CY is 8 pounds. So here we can see that our assumption for CY was correct, 8 pounds. Now, it's time that we can find our value for horizontal component at point C. So we're going to sum the forces in X direction. We have positive Bx. We have negative Cy, all equals to 0. We have already found the value of Bx. That's 1.5 equals to negative Cx. Solving for Cx, it's equal to 0.15 pound. Now for member AB, we are still missing a value for AY. This can be simply found by summing the values of all the forces in y direction. We know By is going to be negative By. Our AY is going to be positive, all equals to 0. We know that our AY is not known, but our By, we just found it. It's negative 8 pounds. So here can be either said it's negative 8 pound, or change the vector and make it positive 8 pound. Now the members CD. For member CD, let's sum the forces in X direction. Sum of forces in X direction equals to 0. Positive Cx, we have negative dx, all equals to 0. We know that our dx we need to find, and we have already found the value of Cx, it's negative 5. So positive on one side comes negative, and the negative from dx cancel the other negative, and finally we are left with 1.5 pounds for value of dx, or horizontal component. Now, sum of the vertical component. Cy is, our vertical component at C is negative, and horizontal component, or vertical component at D is positive. All of this is equal to 0. Horizontal component is negative 8, and we know that Cy is equal to dy, therefore it's 8 pounds. Finally, we need to find the moment, so sum of the forces about the point D. We know there is a moment at D, and there is only one horizontal component at C that's creating a moment, so it's clockwise, so it's negative, so 1.5 times 4 feet equals to 0. Solving for moment, it's 6 pound-foot. This last fundamental problem, determine the components of reaction at fixed or D in the pins A, B, and C of the 3-member frame. Let's draw the free body diagram. BC, a horizontal and vertical component for B. We also have a horizontal and vertical component for member C, but we have to have them in opposite direction as we did in the other problems. Now our member AB. For AB member, we need to make sure that our reactions are opposite for member B. And for A, it's the Cartesian of horizontal and vertical components. And now our member C, CD, it's unique in the sense that our point D is not pin connection but fixed connection. Therefore, there's going to be 3 different reactions. But before we do that, let's do C. For C, it needs to be opposite of whatever we had for reactions. And then for D, in a moment, D. Start with the, and before we start with the calculation, also let's do our point loads. So we have a point load right at B. It's 6 kilonewton downwards, and then 8 kilonewton 2 meters apart, and then another 8 2 meters apart, and finally a 6 kilonewton right at C. Let's start with member AB. We're going to take moment at point B. Doesn't matter, you take it at A or B, but at member B we only have one reaction, that's AX, and it's 6 meters away, all equals to 0. Therefore our member or reaction for AX is equal to 0 kilonewton. Now we're going to take moment about the point A. We have member BX, that's 6 meters apart, and again, because there aren't any other reactions, this is going to be 0 kilonewton. And now we can focus on member BC before we do any other calculation, because our vertical component will be affected by the member BC. I'm going to take moment about the point B. So we have point load at 2 meters away with 8 kilonewton force, and it's counterclockwise. We have another one at 4 meters away, and we have another point load that's clockwise as well, and it's 6 meters away. And finally, we have a reaction for our vertical component for point C, and it's counterclockwise, therefore it's positive, and it's 6 meters away as well, all equals to 0. Solving for this, we get Cy as 14 kilonewton. Now I'm going to take a moment about the point C. There is a point load working counterclockwise, 2 meters away, another one at 4 meters away, and another one at 6 meters away. And then we have a vertical component that's also working counterclockwise, By, and it's also 6 meters away, and everything is equal to 0. Solving for By, we get negative 14 kilonewton. As always, we can always have it as negative 14 kilonewton, or we could switch our vector and have it as positive kilonewton, but as usual, I'm going to keep it as negative. Both answers are correct. Now for member BCS, we're gonna calculate our forces in the x direction. We know we have bx, but we already know that our bx is equal to 0, and then we have our cx, which is in opposite direction, and it's also equals to 0. Solving this, we know cx will be 0 kilonewtons as well. And now let's go to member CD. For CD, we haven't done found the point load, so let's do that real quick. So we know that 1.5 kilonewton per meter, and we know this member is 6 meters long, so therefore it'll be 9 kilonewton, and it'll be halfway through them, 3 meters on each side of the point load. Now let's take the sum of forces in the x direction. For member CD, we know our cx is going to be 0, and it's also positive, and then we have negative 9 kilonewton from our point load. Negative dx equals to 0. Solving for dx, we get negative 9 kilonewton. So now we either can have negative 9 kilonewton or can switch the vector and have it as 9 kilonewton. Either way is correct. Now I'm going to do sum of forces in the y direction. I have dy and I have negative cy, both equals to 0. We found the value of cy, and that is 14. Therefore, our dy will be 14 kilonewton as well. Now let's take the moment about the point D. We know our point load is 9 kilonewton, and it's in counterclockwise direction, and it's 3 meters away. And we have our moment about the point D. All this is equal to 0. Solving for moment D, we know it's negative 27 kilonewton per meter. We can either have it as negative 27 kilonewton per meter, or we could switch the moment direction and have it as 27 kilonewton per meter.